The same is true about brain as well. The remaining tissues need insulin for the uptake of glucose, and for them, they need glucose transporter support. Once the glucose enters the cells, it gets metabolized and gets converted into ATP, and this ATP acts like a metabolic switch, knitting the metabolic function of beta cells and the electrical activity of cell membrane together. So, when the glucose enters, the beta cells have to be excited to secrete insulin. This metabolic switch is mediated by a specific channel, which is called ATP channel, which is the topic of discussion today. This is ATP-sensitive potassium channel. The ATP potassium channel consists of two components, which is AIR 6.2, which is potassium invert. IR is invert rectifying current, AIR 6.2. AIR, invert rectifying channel, potassium channels are 1 to 7. And 6.2 is a particularly subtype of potassium channel. It is also related to the potassium induction inside the myocytes and the phagocytes. And the prolonged QT interval is also mediated by this channel. But I'm not going to discuss that. This metabolic switch consists of two components, the KIR 6.2 and sulfonylurea receptor protein. And there are 4 molecules of SUR1 and 4 molecules of KIR2 which together form this receptor, and these units are arranged in concentric tubes. दो ट्यूब्स हैं एक दूसरे के ऊपर चढ़ी हुई, अंदर की तरफ KIR की ट्यूब है, उसके बाहर की तरफ sulfonylurea receptor की ट्यूब है. अगर आप देखें तो ये आपको यहाँ पे नजर आएगा, अंदर की तरफ नीली ट्यूब्स, the blue tube is KIR1, KIR 6.2, 4 subunits, and surrounding that there is another tube, which is sulfonylurea receptors, 4 molecules arranged around it. So this concentric tube with the central channel which conducts potassium. Once we understand this, let's see the distribution of ATP channels. Obviously, it is in the pancreas for secretion of insulin, but it's also present in the cardiomyocytes. And the prolonged QT interval, once it gets abnormal, is there. The contractility is also controlled by it. And it's also present in vascular smooth muscles and related to development of cholesterol metabolism and atherosclerosis. And this is interesting, we are going to discuss it once we reach the end of this lecture. Because the sulfonylurea receptor is also present in KIR1, the sulfonylurea drugs act through this receptor. The sulfonylurea binds to this receptor and it modulates insulin secretion by this channel stimulation. Sulfonylurea receptor protein is a very interesting protein, and I will develop on it for a short period of time. It's ABC protein, ATP binding cassette protein, and this is very interesting protein because this has been present from fungi and bacteria right up to the human being. It's responsible for energy-dependent excretion of drugs. Not only does it produce its effect in sulfonylurea receptors to produce an uptake of insulin, in most of the fungi and bacteria, it is also responsible for excretion of antibiotics and development of drug resistance. It is also in the cancer cells, the same protein is responsible for excretion of cytotoxic drugs and produce drug resistance in cancer cells. It is also the same sort of protein which is conducting intracellular cholesterol outside, and HDL is produced by the same mechanism. So this is a very diverse protein, and sulfonylurea receptor belong to this ABC class 8 gene. Sulfonylurea are of 3 types, type 1 and 2. The 2 is further subdivided into A and 2B. Not very interesting, but intracytoplasmic component of this sulfonylurea receptor, which has got 17 transmembrane domains, have got a fold which can bind ATP. And if you see that, the NDF1 and NDF2 nucleotide binding fold 1 and nucleotide binding fold 2 are the sites where ATP gets bound to this receptor. And once the ATP binds to this receptor, it constricts and closes the bone. ATP binds to the site and it would close the potassium channel, and it not only binds ATP, it also binds sulfonylurea. And sulfonylurea therefore mimic the action of ATP by closing the channel. Now, the second protein is KIR, potassium invert rectifying channel. Let's start. What is that? KIR is specific potassium. It only allows potassium ion to move through it. And movement of potassium is whenever you think about potassium, intercellular potassium is high and extracellular potassium is low. So the concentration gradient determines the direction in which potassium is going to move. Because of the high intercellular potassium concentration, the basic direction is from in to outside of the cell. And this is the natural gradient. But what happens if the channel is biased? In a non-biased channel, the potassium will move from inside to out. But if the potassium faces a channel which is biased, it will facilitate movement of potassium in one direction only. And this is what happens in KIR 6.2. The KIR 6.2 channel is invert biased. It allows the potassium to move inwards with 3 times more facility as compared to outwards. ये पोटेशियम को अंदर जाने की इजाजत आसानी से दे देता है, बाहर निकलने की इजाजत नहीं देता। हालांकि पोटेशियम अंदर ज्यादा है और बाहर निकलना चाहती है, लेकिन ये चैनल इनवर्ट बायस्ड है, ठीक है। पर ये पोटेशियम को बाहर निकलने की इजाजत खास नहीं देता, थोड़ा थोड़ा तो निकल जाता है, लेकिन अंदर जाने की इजाजत बहुत देता है। लेकिन इसके साथ अगर आप एक और भी देखें कि पोटेशियम का रेस्टिंग पोटेंशियल -60 मिलीवोल्ट है, ये नेगेटिव पोटेंशियल है, और पोटेशियम पॉजिटिवली चार्ज आयन है, तो ये नेगेटिव पोटेंशियल क्या करेगा? ये पोटेशियम को बाहर से अंदर की तरफ खींचेगा। और अगर आप इन 3 चीजों को देखें, take the 3 things together, we have got a potassium which is present across the membrane, where the channel bias which is invert, which is allowing the potassium to move inward with more facility, which is invert bias. The negative potential is pulling the potassium in, but the potassium concentration which is high inside is trying to push it out, so 3 forces are acting in tandem. One force is trying to push it out, 2 forces are trying to pull it in. The net effect of the outward force, which is the concentration gradient, is much greater than the combined effect of inward pull of negative electropotential channel bias. And potassium equilibrium can be now calculated by using all these 3 components by Nernst equation. Nernst equation determines the potassium accumulant potential. This is the potential where the electrical potential where potassium movement is exactly balanced. Potassium is not moving out or in, जहाँ पे न्यूट्रलाइज हो जाए। और वो कहाँ पे होगा? जब इनवर्ट इलेक्ट्रिकल पोटेंशियल -90 पे पहुंचेगा, इतनी पुल अंदर की तरफ हो जाएगी, आप पोटेशियम बाहर मूव नहीं कर सकेगा। लेकिन नॉर्मल रेस्टिंग पोटेंशियल -60 होता है, and once the